Now there's another limit that's going to be very important to us that is somewhat similar to the previous limit, and that's to look at the cosine of x minus 1 all divided by x as x is approaching 0. It turns out that this particular limit is equal to 0, and we can obtain it with a little bit of algebra from the previous limit. So let's use the idea of taking the limit that we're considering, cosine of x minus 1 over x, and let's use this idea of fancy ones. In other words, we're going to take that expression and we're going to multiply it by 1, because that leaves the value unchanged. But we're not going to multiply it by just the number 1. We're going to multiply it by something divided by itself, which I call a fancy one. And in this case, what we're going to multiply our expression by is cosine of x plus 1 divided by cosine of x plus 1. The reason for this is it's going to take the numerator, and when we do this distributive property of cosine times cosine, cosine times 1, negative 1 times cosine, negative 1 times 1, and simplify, that numerator is going to become cosine squared of x, or cosine of x times cosine of x, minus 1. The reason that that's helpful is our unit circle gives us what's called a Pythagorean identity, telling us that the sine squared of x plus the cosine squared of x is equal to 1. It's called a Pythagorean identity because way back here when we talked about the unit circle, the cosine of x is the length of this side length of the triangle. The sine of x is the length of this leg of a triangle. And we know by the Pythagorean theorem that the sum of the square of this and the square of this is equal to the square of the hypotenuse. And the length of the hypotenuse is 1. 1 squared is 1. And that's where we're getting that identity cosine squared of x plus sine squared of x is equal to 1. Rearranging that Pythagorean identity until we have cosine squared of x minus 1, what that's equal to is the negative sine squared of x. And that allows us to replace this complicated numerator in this expression with just the quantity negative sine squared of x in the numerator, and the denominator would be x times the quantity cosine of x plus 1. Where this becomes helpful is we can take that negative sine squared of x and break it up as sine of x times negative sine of x. And then we can break up our fraction until we have a sine of x over x limit as x approaches 0, where this is useful because we just figured out what this limit ought to be. Now this second limit, as x approaches 0 of negative sine of x over cosine of x plus 1, that's a limit of a continuous function divided by a continuous function. Because our numerator in that function is approaching 0 as x approaches 0, and our denominator is approaching 2 as x approaches 0, we can replace the values of these functions with this limit to make this whole second limit right here equal to 0. Our first limit over on the left is the one we just worked so hard to compute. So we're going to replace this quantity here with 1 and this quantity here with 0. Altogether, that makes this complicated limit equal to a 1 times a 0 over 2, which turns out to be 0. Now, most other trigonometric limits that you may want to consider, if you can break them up into limits that look like sine of x over x as x is approaching 0, or if you can involve pieces that look like cosine of x minus 1 over x as x is approaching 0, there are many, many other trigonometric limits that you could build out of just these two limits alone. And that makes these two limits particularly powerful and worth remembering if you're going to be considering other trigonometric limits. In many ways, it's analogous to how we can build all the other trigonometric functions out of just the sine of x and the cosine of x. We can build a whole bunch of other trigonometric limits out of just the previous limit. The limit is x approaches 0 of sine of x over x. And this limit right here, the limit is x approaches 0 of cosine of x minus 1, all divided by x. So these are two trigonometric limits that are particularly worth remembering.